So last class, actually, can I get the door closed, please? Could you close the door, please? Last class, we were working on this problem here about doing our simulation. I believe together we got through all of A. Is that correct? Okay, so where we left off is we were talking about actually going through and doing this. We reviewed our rules on how we generate random numbers in our calculator by saying you go to math, probability, and since we don't care about repeats, or repeats don't bug us, we're going to go to 5, and I said 1 to 6, something nice to count by, and I just started working through, and we would say, okay, for this one, since we're going until our first 1, that's 3, this one would have been 8, 3, and I would just write down those numbers. And you would write them down as you went through it. And you were to have done that 30 times. But this is where we kind of ended. To pick up with what C and D are talking about. C says, based on your simulation, estimate the probabilities that you might win on the first roll, the second roll, the third roll, etc. So what that's saying is we're talking about the probability X is the number of rolls, and P of X is for each one of those. What's the fewest number of rolls it could have possibly taken you to get a 1? 1. And then it would have just gone up from there. And you would have just gone and gone and gone until whatever the biggest number that you saw was. For mine, let's just kind of take a guess. If I had 30, let's say I had 3 of those 30 happen on the first roll. Let's say 2 out of 30 happened on the second. I don't know, 1 out of 30. But that's basically what you would do, is you would say, how many did you actually have at each of those stages? Does that make sense? That's because it says, based on your simulation. Based on your simulation, what should you get? The actual probability model is a little bit different, though. When we're talking about the actual probability model, they're saying, okay, how would math on this work out? So again, we're saying that X is going to be the number of rolls. And I'm going to say P of X, I'm doing this vertically for a reason. You'll see why in a second. Is going to go like that. And again, the fewest number of rolls it could take is how many? 1. What's the probability that you will stop on that first roll? What is it? 1 out of 6, because that means the probability of getting a 1. So that's 1 out of 6. If it takes me 2 rolls, how do I calculate the probability that it takes me 2 rolls? Means we don't get a 1 on the first one, and then I get a roll on the second one. Okay? Well, let's actually do this math for it. So 1 out of 6, that was 0.1667. 5 out of 6 times 1 out of 6. That gives me 0.1389. If it took me 3 rolls, how would I calculate the probability that it took me 3 rolls? 5 out of 6 squared, and then 1 out of 6. So basically I need to times that by 5 out of 6. So that's 0.1157. What about if it took me 4 rolls? 5 out of 6 cubed times 1 out of 6. And that would give me 0.0965. And I could really just keep on with this. And without doing the math, let's see here. So 5 would mean I failed 4 times. And then I got it on the 5th shot. 6 would mean I failed 5 times. Got it on the 6th. And those would just keep going, right? What is the maximum number of times it could take me to get a 1? Rolling a die. in reality? An infinite. There isn't one. Does that mean I'm going to keep drawing this out until I get to infinity? You can't get to infinity, and to keep going would be pretty ridiculous. So what you do is you do start working through these, and you start calculating. This would be 0.08 basically. This would be 0.067, 0.056, 0.047. Once you hit a probability right here, you're going to go, it's okay to stop when your probability is finally less than 0.05. Does that make sense? All these guys are smaller and smaller. I need to write out the model until you get to that 0.05. That 0.05 is our level of significance that we're going to be talking a heck of a lot about. So I got a value that's less than 0.05. And then how do I find out what's supposed to go with this, though? Because my probability model has to do what? Add up to 1. So for this piece here, I'm going to do 1 minus all you found for what's left. And when you do that, you are going to get a slightly bigger number, but that's okay. Because I don't want to sit here forever, frankly. You could go at this for a really long time. Usually the rule is, when can I stop? If you're trying to make out an actual probability model and you have an infinite number of ways you can do it, keep going until your probability gets down to a little bit less than 0.05, sorry. Does that make sense? Okay, that's a lot of work, isn't it? This was not less than 0.05, right? So I had to do it one more time. This is less than 0.05, so I can stop. But my probability model has to add up to 1, so it means I have to figure out what the rest of it is. So this is 9 and everything greater. Okay? Now there's a really big problem with this. If I wanted to calculate the expected value, if I wanted to plug this into my calculator, calculate the expected value, I wouldn't be able to do the whole table. So we've got to have other ways to do that. Here we go. This is what we've always just done. And that is using what's called a geometric probability. Now, geometric probabilities, this is very important. Geometric probability means that I'm starting with this Bernoulli trial. And Bernoulli had what? What did you need for Bernoulli? Before that, very first thing we need. 2 possible outcomes. You could think about it as good or bad, yes or no, ones and zeros. It's got to be binary. And just be careful, don't think that success is saying, hey, I got a good one. Success just means you met the condition we're talking about. So we have to have that binary. Then what did we have to have? Independent. So if it was something simple like flipping a coin, every time I do that, it shouldn't affect what happens next. But when we're pulling from a group, when we're drawing without replacement, like I'm going to select people to be on a committee, you've got to be really careful. Or even if I'm pulling people out to survey to get a good representation. And when we're talking independence, you are not going to go over 10% of your population. And that 10% rule is going to stick around with us. And then the very last piece that kind of goes with this is why we need independence. Right, so that your probability doesn't change, that your probabilities are all the same. Something is a geometric probability model if our question is asking me for how long does it take for me to be successful. I kind of think about this. Geometric, you'll hear me say this a lot, is go until. Go until you have a success. I'm going to stand here and I'm going to shoot free throws until I actually make one. We might be here for a while. Not that good. I mean, come on. We can practice all we want. That doesn't mean we're going to be perfect at everything we do. I could run every day and I'd still be beat by a third grader. Those kids are fast. I'd be like, chicka. No? Okay. So when we're doing a geometric probability, we use this little mnemonic device to kind of help us remember. Fits. And actually, the B, the I, the S, that's just your Bernoulli. So anyone? Arg. Hang on one sec. All right. Or when is your dismissal for? Okay. All right. So when we're looking at this, the B, the I, and the S are your Bernoulli requirements. So what was my first one for Bernoulli? One more. 2 answers. And binary. Binary is what we think about for that one. What do you want to guess I stands for? Independence. And that's the idea that your trials must be independent. The only reason why we're doing it in this order is because it spells something. There's really no requirement for what order you do this in. But the T is what makes something a geometric model, because we're going to have geometric and we're going to have binomial. T stands for trials. And that's because that's what I'm looking at. I'm trying to count how many times it takes me to be successful. And anybody want to guess what S stands for? Your 6. Yeah, your 6 swag. Okay. So your S stands for the fact that your probability of success should not change as you go through it. So you know you're dealing with geometric when you already have your Bernoulli in place. So it's binary, it's independent, probability of success doesn't change. Geometric, you can either think about it in either way. Either count your trials, or I like to think of it in terms of go until. But it's whichever one of those works for you guys. And you're going to have to keep that straight. Okay, it's just something you're going to have to memorize. All right, back to the independence. This is going to be something that kind of affects us more than anything else, and it's not going to stop. This idea of independence is what this entire class is based off of. Everything we do in here is situated on this idea that one outcome is not going to affect the other. Otherwise, all the rules that you learn in here fail. They don't work. I can't use them. There is a whole bunch of statistics that you can do for non-independent stuff, but that ain't this class. That's a more advanced statistics class. Okay, so independence is hugely important. So if we know things are independent, like I know rolling a dice, one outcome should not affect the outcome others as long as it's a fair dice. Same thing with flipping a coin. One shouldn't affect the other if they're fair coins. So far, so good? But then there's that draw without replacement. Flipping over a deck of cards. I'm pulling, let's say I've got a whole bunch of little balls in a bag, and the balls are colored, and I pull one out, and I pull another one out, and I pull another one out, and I want to know the probability. Those guys need to be independent, but when I'm pulling something out without replacement, your probability is going to consistently change. Remember the batteries problems? It's like, okay, 7 good batteries, 3 bad ones. What's the probability? Every time you put one out, you have one less in the bag. So your probability is changing. For us, what we say is as long as our sample is less than 10% of the whole entire population I'm interested in, you're okay. Like, how big is the senior class? 759, give or take? So if I wanted to do a survey on the senior class, what is the most number of people I could actually survey and still consider them independent? 75, which is 10%. If you go over that, you're now starting to affect, because it's talking about the people that are left are going to have issues. So that 10% should be okay as long as you know there's like no bias going into your selection process. As long as you're random. So randomness and independence and 10%. These guys are all linked together. Okay? So read through this problem. Okay? What do you think? Can you consider them to be Bernoulli? First requirement for Bernoulli? 2 answers, binary, success, failure. Does this work for that? Lost or not lost? Now, we wouldn't consider it like lost to be successful. Yay, they've successfully lost my bags. But that's just the characteristic that we're looking for. Okay, so don't think good and bad. Just think looking for not what I want, what I don't want. Okay? So we have that. So really what we're asking here is the whole idea of independence. We're looking at, is the probability going to change? Anybody want to take a guess? Traveling with a group of 22 people. The fate of your bags, are your bags going to be independent? No? Why not? They'll all be near each other. Good. And if you're not a traveler, you might not have any idea about this, but you're absolutely correct. Right. Yeah, they're all checked in at the same time. They're checked in by the same person. They're probably handled by the same baggage people at the same time. If you are going from here to Australia and you have like 3 layovers, your bags are going to have those 3 layovers also. Those exact same times to get lost. Whereas the other people on the flight might not be the same. So what's really kind of interesting is if you're flying with a big group and you lost 1 bag, odds are you probably lost more than 1 bag. Because all of your bags were handled the same. But from person to person, check-in to check-in, destination to destination, the probabilities might change. It just so happens that out of 1,000 bags, they misplace on average 5. Doesn't mean everybody has a 5 in 1,000 chance of having their bags lost. Some people have a lot higher chance. Always be careful with who you travel with because there's some unlucky people out there. No, nothing. How many of you guys have ever been on a plane before? Been on a plane with a connecting flight? Okay, this is when you need to worry. That's why you always want to make sure that you have enough time between flights, because some people will be like, I don't want to sit in the airport for a really long time, so I'm going to have an hour layover, which is a great goal. But if your first flight is delayed by a half an hour, now your layover is down to 30 minutes. That means your bags have 30 minutes to get from point A to point B. You might be able to run it. That doesn't mean that your bags will. Okay? And sometimes you have to get your bags if you're switching between airlines or if you're going from an international flight to one within country. Yep, you got to be careful. All right, so what's in yellow here is what's really, really important. Because I'm not going to sit there like that problem that we had with rolling a dice till you get a 1. Because I'm not going to sit here and type in an infinite number of things into a table to try to figure out what my expected value and standard deviation is. That would really stink. We actually have formulas. These are the formulas for geometric probability. That means before I even go to try to touch any of these, I have already checked and written it down, because if you didn't write it down, it didn't happen, that my events are success or failure, independent, the probability doesn't change. We denote the probability of success, what you're looking for, not necessarily good or bad, as a P. Some textbooks don't even bother with Q. Some textbooks do P and the opposite of P, 1 minus P. I figure, hey, Q is a lot easier to deal with. Either you got it or you didn't. They add to 1, boom. Okay? Capital X is what you're going to define as the number of trials until your first success. So how you calculate the probability, this is what we did on that table. We said, hey, if I had to roll the dice 4 times to get a 1, that meant the first 3 times I did not get a 1, and then on the 4th time I did. So that's why it's X minus 1, because you failed until that last one you finally got it right. Expected value. What's another word for expected value? Mean. It's another word. Average. Very nice, simple problem. If there is a 50-50 chance that I'm going to flip a coin and land on heads, how many times should I expect to have to flip it in order to get a heads? Twice. There's a 50-50 shot. You can generally expect to do it twice, and one of them should be heads. Does that mean that one of them will be heads? No. That just means in the really long run, if it's a 50-50 chance, you'd probably need to do it too. Okay, 1 over P. Standard deviation, nice, straightforward equation. Square root, because remember, we only do math on variances. That means this in here is the variance. So standard deviation is the square root of Q over P squared. These formulas you need, but luckily for you, these formulas are also over here. Expected value, standard deviation, they write it a little bit differently than we do. Okay, I don't know why they do it that way. He's just weird. Yeah. Okay. You got my yellow stuff? Got the yellow fellows. Okay. Let's do some math. Chips. Not talking about potato chips or chocolate chips. Though I'd really like to have chocolate chips, especially in cookies. Because that's yummy. Read the problem. Read it. You got that problem read? Now, I'm not quite sure what's going on in your heads, but it seems like no matter how many times I tell you, you must show this, y'all don't. Ah, she's just kidding. I don't need to show that. I'm just going to get right to it. For these problems, no matter what, before you do any of this, you must be able to explain to me what kind of distribution it is and why is it that distribution. So the first thing that we need to know, is this going to be Bernoulli? For Bernoulli, what do I need? Binary. Okay, so basically I'm what or what in this case? The chips work or not? Since we're looking at the bad ones, I'm actually going to define my probability to be getting a bad chip. Okay, so it's either a yes or a no with that. So I can talk about probability here. What else do I need? Independence. So what do you think? Is having one chip bad affecting the next chip? No, they don't run around smashing each other to just make you feel as bad as they did. It'd be really weird. So what we're going to say is we're going to have to assume, and we're actually going to be doing that a lot in this class. We're going to have to assume the chips are independent. And what's the next thing? Probability. So what is the probability of getting a bad chip? 0.02. And since what we're talking about here is a first bad one you find, this is a go until problem, that tells me that I can use the geometric model where my P is 0.02. That is your work for this problem. That is required to be shown. If you do not show that, what do you think is going to happen? You're going to lose points. Show me what we're talking about. Why can I do it as binary? Because you either get a bad chip or you don't. Talk about independence. Give me your probability. And when it is a go until problem, that means we can use geometric distribution where your probability of success is 0.02. That tells me I can use the formulas that I just had. Because I've done that, I can now do this stuff. All right? So now that I've got that, let's think about the work. It says for A, what is the probability that the 5th chip you test is the first bad one you find? So now I'm looking at for the probability that X is 5. It takes me 5 times to get there. How do I calculate that? What? 0.98 to the 4th, good, times 0.02. This little guy minus 1, because I failed that. I went, whoops. I went, good chip, good chip, good chip, good chip, bad chip. Yes. Because that's what I'm talking about. Don't think that success is a good or a bad thing. Success is just what is the characteristic you're talking about. I'm talking about how long it takes me to find a bad one. So that's why I define it as 0.02. You can define success here if you'd like as 0.98. Then you just have to be careful when you go through and you work your problems which one comes first. Okay? Can somebody tell me what that works out to be to 4 decimals? Beautiful. Thank you. Now for B is saying what is the probability that you find a bad one within the first 10 you examine. Does that mean that you have to find the bad one on the 10th one? What about on the 9th one? Can be anywhere, right? So I could think about this. This could really suck. I could say, think about it as the probability that it happens on the first one, that it happens on the second one, that it happens on the third one. Oh, dear God, until the 10th one. Anybody want to do that? Or an easier way to do this is to just say 1 minus the probability that they're all good. That's too hard. Flip it around and say 1 minus the probability that they're all good. What's the probability of good? 0.98. How many? 10. So the probability that there's at least one of them in there that's bad, remember that's the at least, means 1 minus the probability that they're all good. That ends up being 0.1829, I believe. And as is always the case, and ladies and gentlemen, this is the hardest unit for many people. This unit is the reason why most math teachers refuse to teach statistics. That should tell you something. Okay? It's not easy, and it's the context. Any math teacher could follow a formula. But understanding what it's talking about when it's in context, that is very difficult. That is critical thinking, and that's what we're trying to get you to do here. All right? So you can even see here, even in the textbook, they spell it all out. Then they get to do the math. You don't get to do the math unless you've solved it out. This says use a geometric model on a calculator. It's actually a little bit harder to use the calculator here, so we're not going to do that quite yet. It's easier to do it by hand. Okay? Abso-freaking-lutely. I never write that in a paragraph form. I'm like, are you kidding me? I'm not going to do that. And what's really nice is once you've done that, so I did that for this, any other problem that deals with that same situation, I don't need to do it again. Even if, oh my gosh, it's another problem. See, because this one's the same thing. How many do you expect to test before finding a bad one? How do you do that? Beautiful. That's it. So this is the expected value. Is 1 over p, so 1 over 0.02. And what does that give you in math? I heard it. 50 what? Chips. You probably will have a bad one in 50 chips. Heck, they might all be bad. They might all be good. But in the extreme long run, that's what you expect, 50 chips. Okay? All right, read through this. We've got, I think, this problem and then one more. Yep, this problem and one more. And ladies and gentlemen, this gets a little bit tricky because we are talking about everything that we have done in probability thus far. Everything we have talked about at all in this class. I'll tell you, in pre-calculus, my students have a cumulative portion of each test. Every single test has a cumulative portion. Y'all don't have that because it's built into every question. Okay, so it's not like you're never seeing this again. It just comes up again in a slightly different way in the next unit. What am I going to consider a success for this problem? I'm sorry? Not just any donation. $100 donation. Okay, does that make sense? My success here is a $100 donation. That's what I'm curious about. That's what I'm asking. I'm asking you about how long until she gets a $100 donation. How do I calculate the probability of a $100 donation? Or what is the probability? Probability of a $100 donation. 0.05? Which one is it? There you go. Absolutely right. Very good with that, by the way. What he's talking about here is the first thing I want to do is I want to find the probability of a $100 or more donation. If I think about that and what we've talked about before, that's also the probability of getting $100 times the probability, I'm sorry, it's backwards. We have to first start with the idea that they actually donated. It's a probability that they donate times the probability that they get $100 or more dollars, given they've donated. So what was the probability that they actually donated? 0.2. Probability that they gave $100 knowing that they donated? 0.05. So that means my P here that I'm talking about is going to be what? 0.01. I was hearing 4s and I don't quite, and I was going to write down a 4 because I was saying that. 0.01. So we have the probability of a $100 or more donation is 0.01. What else do I need to talk about? Independence. What do you think? People's donations? Where we're calling? Yeah, so I'm just going to say that. I'm going to say donations should be independent in context. Donations should be independent. Now, I'm trying to use my formulas here. In order to use my formula, what do I need? Geometric. So since this is a go until, I can do geometric where my probability is 0.01. So how would I calculate the expected value of this? So it should be 100 contacts. And actually, we're running out of time here, but that's okay. All right. So we didn't get to this very last problem. That's not too horrible. The answers are all going to be posted. What I need to make sure that you guys understand is when you're writing these out, you have to write out your assumptions and conditions. As of right now, we've done enough to where you can do those first 3 bits from the Khan Academy assignment. Okay? Thank you guys for bearing with me. Y'all have a good day. No. Wait, I don't know. Are they? Okay. Yeah, but there's only 24 problems. It's 4 questions apiece.